Hello, good day. This is John Vincent Di Lerano, and today we're going to be talking about the most common patterns in nature, which includes symmetry, fractal, spiral, and tessellation. So the first thing that we're going to tackle right now is about symmetry. Symmetry is a pattern that shows reflection of images, and there are two types of symmetry: radial and bilateral symmetry. Bilateral symmetry is a concept that two opposite sides have identical features. For example, bridge and a butterfly. On the other hand, radial symmetry is formed around an axis. For example, a starfish. The second most common pattern in nature is a fractal. It is a pattern which repeats at progressively smaller sizes and angle. For example, the Pascal's triangle, or fern, and a snowflake. The third most common pattern in nature is spiral. This is a pattern that moves around a central point and continuously widening. For example, seed of a sunflower, waves, or a snail shell. And the last part, or the last most common pattern in nature, is tessellation. It is a pattern that repeats figures closely fitting together with no open gaps in between. For example, the honeycomb and the sweet fruit, pineapple. So the next lesson that we'll be tackling is about variables. So this lesson will introduce some of the special languages, or the special languages, which are the foundation for much mathematical thought, such as the language of variables and the language of sets. Variable, for example, is like a box of crayons. It contains a lot of different colors, but it didn't give a specific one unless we pick one color we want. A variable is known as a placeholder. Either it has one or more values, but is still unknown, or it has so many different values that satisfies the condition and can make a statement true. There are actually three most important kinds of mathematical statement. The first one is universal statement, the second one is conditional statement, and the third one is the existential statement. A universal statement is a property that is true for all elements in a set. For example, every negative number is less than 1, which is actually true. Why? It is because a number that is less than 1 is actually a negative number. The next one is conditional statement, which is a property that if it has one element that is true, then some other element has also to be true. For example, if 180 is divisible by 60, then 180 is divisible by 12. The third one is existential statement. This is a property that shows the existence of at least one element in a set that could make a property true, given a property that may not be or may be true. Just for example, there is a positive number that its square is equal to itself. Now let's move on to the combination of the mathematical statements that we have already defined. First is universal conditional statement. This is a statement that consists of the word for all, which represents the universal statement, and the word if then, which represents the conditional statement. Just for example, for all numbers n, if n is greater than 1, then n cubed is greater than n squared. We can actually rewrite or rephrase the universal conditional statement in two ways, which we can use the word for all and the word if then. First, For all numbers n greater than 1, n cubed is greater than n squared. Or, if a number n is greater than 1, then n cubed is greater than n squared. The next one is the universal existential statement. The first part of this statement is using the universal quantifiers like every, all, and each, while the second part of this is stating the existence of something which satisfies the existential statement. For example, all integers have a positive square. We can actually rewrite or rephrase that statement. For example, every integer has a positive square, or for all integer n, there is a positive square for n. Or, for example, for all integer n, there is an integer x such that x is the positive square for n. And the last part is the existential universal statement. The first part of this statement declares the existence of a certain value. On the other hand, the second part states that a certain value reaches the satisfaction of a certain property that applies to all things of a certain type. For example, there is a negative integer that is greater than or equal to every negative integer. And that statement could also be rewritten or can be rephrased by the following format. Or there is a negative integer g that is greater than or equal to every negative integer. Or there is a negative integer g such that every negative integer is less than or equal to g. Or, for example, the last one, there is a negative integer with a property that for all negative integers h, g is less than or equal to